Hello, Mr. Claudia here, and today we start calculus. Dun dun dun. This is Unit 2, differential calculus. Unit 3 is integral calculus, which is the part that we don't do in the regular grade 12 program. This is Unit 2. Technically, we're doing 2.1 today. So I have, Unit 2 is divided into 2.1, which is the idea of limits, which is the how, or why calculus works. And then chapter 2.2 is the derivative, which is the how we find how we do calculus. And then in grade 12, we're going to do applications, which is kind of all the neat things we can do with calculus. So I like to say that what we do in grade 11 is kind of the meat and potatoes of calculus. So today we're looking at limits. And, we should always say that we want to push it to the limit. Push it to the limit. So let's get started. The limit is a kind of a confusing concept. So I find the video hopefully will be helpful to kind of re-listen to if you're having trouble getting the concept. Consider the function f at x is equal to this. So it's actually a quadratic function. What is f at 4? Well, this is no surprise, no trick question. We just want to figure out what the value of the function is at x equals 4. So what your teacher taught you is to sub in 4. So then you replace all the x's with 4. So then we solve this by order of operations. So we have our bedmass. So we have 2 squared plus 3, that gives me negative 4 plus 3, so I end up with negative 1. So that negative 1, that is the value of the function at x equals 4. Okay, that's something we've always done, we always know. Now instead of looking at the function at x equals 4, let's look at the limit as x approaches 4. So what happens to the function as we get closer and closer and closer to 4? So let's sub in all these numbers. Now I'm going to get my calculator for this. This is kind of a proof, right? I'm showing you how this works. So let's say I'm getting closer and closer to x from the left, right? I'm taking numbers that are smaller than 4. So 3.5 and 3.9, 3.99, 3.999. I'm getting closer and closer and closer to 4. So I have 3.5, so I'm going to sub that in like I just did. So I have 3.5 minus 2 squared, and then I have 3 minus that number, so I get 0.75. You can do the remainder by yourself. Pause the video. Okay, and if you type the rest into your calculator, you're going to get negative 0.61, negative 0.9601, negative 0.9960. So let's look at this. As my x values get closer and closer and closer to x, what happens to my y values, or the value of my function? Well, it starts at 0.75, then it goes negative 0.5, 0.6, negative 0.96, negative 0.99. So it's getting closer and closer, it looks like, to negative 1. I don't know what happens at x equals 4, but I know it looks like as I get closer and closer, the function is going to be negative 1 when it gets to x equals 4. So this is kind of the introduction of the limit, and this is the language we want to get used to. As we approach x equals 4 from the left, y, or the value of the function, approaches negative 1. Similarly, what happens as I approach the function, or approach x equals 4 from the right, numbers that are greater than 4. So 4.5 and 4.1, 4.01, getting closer and closer and closer to 4 from a larger number. Let's do the first one together. So it's 4.5 I'm subbing in, minus 2 squared. Then I take 3 and subtract that answer. I get negative 3.25. If you do the rest yourself, negative 1.41, negative 1.0401, negative 1.0040. Okay, so what do we see? Let's do a similar thing here. As we approach x equals 4 from the right, y approaches negative 1. Right? Because we're getting closer and closer and closer to negative 1. I don't really know what happens at x equals 4 when I'm talking about the limit. I just know that it looks like my y value is going to be negative 1 when x reaches 4. So we would say, therefore, because from the left and the right they both seem to approach negative 1, therefore the limit of f at x as x approaches 4 is negative 1. And let me just try to hammer this home. Let me graph this. So this was a quadratic opening down with vertex 2, 3. This is 2, and this is 3. And 4 is somewhere over here, and we know the point is negative 1. So there's a difference between the first thing we did, which was sub in 4, and the second thing we did, which is the limit at 4. Subbing in 4 says, hey, I want to know exactly what the y value is at x equals 4. So if you want to think of an analogy, you take a plane and the plane parachutes you down at x equals 4, and then you figure out that you're at a y value of negative 1. That's what we've always done with math. Now the limit is what happens as you get closer and closer to 4. So instead of taking a plane, you're driving along the function. And the question with the limit is, well, where does it look like you're going to be when x equals 4? The answer is, it looks like I'm going to be at negative 1. Same with the coming from the other side. It looks like when x equals 4, I'm going to be at negative 1. The limit, we don't care what actually happens at x equals 4. We only care about what happens as we get closer and closer from either side. I draw that kind of arrows to show from the left and from the right. Now, for a question like this continuous quadratic equation, the limit at x equals 4 is negative 1, and the value at x equals 4 is negative 1. So it's kind of they're the same number, and this whole process seems like a waste of time. Let's do the second example, the rational expression. Consider the function g at x is equal to this very difficult rational function. What is g at 3, and what is the limit as x approaches 3? Okay, well, to find g of 3, that's easy. I can do that. Sub in x equals 3. This is what your teacher taught you last year. G of 3 is equal to 3 minus 3 over 3 squared minus 4 times 3 plus 3. That gives me 0 over 9 minus 12 plus 3, which gives you a 0 over 0 situation. This is a big problem, right? Alarm bells are going off. This does not exist. This is indeterminate form. Determinate form. It's a fundamental math problem. There is no value of the function at x equals 3. If you were to be helicoptered in to x equals 3 and you were dropped down on the function, you would plummet because there's no function there. There's nothing there. There's some sort of discontinuity. Let's look at the limit. Now the limit, the idea of the limit is, okay, let's look at all the values as x gets, the values of the function, as x gets closer and closer and closer to 3. So from the left, smaller than 3. So 2.5, 2.9, 2.99, blah, 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 blah. Do you want to do this? Sure, let me do the first one. So it's 2.5 minus 3 divided by open bracket 2.5 squared minus 4 times 2.5 plus 3. That gives me 0.667. You can do that with all the rest, and you should. You should do the exercise. 0.5263, 0.5025, 0.50025. Huh. So it looks like as my x values get closer and closer to 3, my y values get closer and closer, it looks like, to 0.5. You could keep going and check, but it looks like it. Let's look at from the other direction. So I'm going to take numbers that are slightly bigger than 3. So starting with 3.5, 3.1, getting closer and closer and closer. If I sub these into my expression, it looks like, when I do my calculations, it looks like as the numbers get closer and closer to 3, my y values get closer and closer and closer to, again, 0.5. Well, this is great. We say then the limit of g at x as x approaches 3 is 0.5. That's how we say this. The way we write it in math lingo is the limit as x approaches 3 of the function. So the limit of the function as x approaches 3 is 0.5. Now, we can't graph things like this. Remember, I told you you're never going to get a rational function like this in IB, but I can tell you what it looks like. It looks like this. And like this. So it actually works out to be a rational function. If you remember from grade 10, you're going to cancel out some factors here. And so it is actually, it looks like a regular rational function. But there's this problem. There's this discontinuity, this hole. At x equals 3, there is no function. There's a hole there. So at x equals 3, as we found out, it doesn't exist. But the rest of the function exists. And the limit exists. As I go along the limit and I get closer and closer to x equals 3, it looks like my function is going, the y value is going to be 0.5. Now remember, the limit, I don't care what happens at x equals 3. I just look to think about where it's, or look at where it's going to go. Similarly, from the right, as I get closer and closer and closer to x equals 3, it looks like my y value is getting closer and closer and closer to 0.5. So that's why my limit is 0.5. Let me use my analogy again. With this function, and if I want to find out the value of the function x equals 3, that's like taking a helicopter or a plane and it drops you at x equals 3. Well, it would drop you at x equals 3, but there is no function there, so you would fall like down to and crash. Whereas the limit is talking about what happens as you get closer. So that's like driving. If you were driving along this function, where does it look like you're going to end up when x equals 3? Even though there's a section of road missing here, it still looks like when x equals 3, you're going to end up at 0.5. That's what the limit's all about. So notice the difference between the two of these. In this graph, there is no y value at x equals 3, but there's still a limit at x equals 3. The limit is 0.5. So that's our introduction to the limit. Now let's start manipulating it. So oh sorry, what did I write here? Sorry, I just made a little note about approaching from the left. And the approaching from the right. That's fundamental to our analysis of the limit. We look at both directions. Okay, so we define limit of a function. The limit of a function as x approaches a is equal to L. And let's write that out one more time. The limit of f at x as x approaches a is equal to L, to the number L. Remember this word approaches is fundamental to calculus, it's fundamental to the limits. Approaches is x gets closer and closer to a, but not equal to a. Okay, so here are a bunch of properties of the limits, and I don't get you to write these out. In general, all the properties are pretty similar to the properties that you've learned about other functions. So the limit of a function plus a function, you can separate them out. You can distribute the limit. So you have limit of f plus the limit of g, or you could do subtraction. If you have a constant multiplied by a function, you can take the constant out, factor it out, and just take the limit of the function. The limit of two functions being multiplied, you can multiply the limits of each separately. Similar division, similar root, similar square root, or sorry, similar exponent or square or root. Don't worry too much about these. Just know that limits behave pretty similar to other things we learn in math. The only real important one is this. The limit, actually we have two important ones. The limit as x approaches a of the function x is equal to a. Now that's confusing. I'll do a quick explanation of what that means. Here's my y, here's my x. Well, if you have a function that's just x, right? Remember, this is the function. So the function f looks like something like this. Sorry, the function f of x equals x is just a line. Then as x approaches a, which is some value on the line, well, the y value is going to be the same, right? Because this is that just there's the slope of 1. So that's one property. If it makes sense to you, great. If not, that's kind of just what you have to remember. The other one is this. The limit of a constant is a constant. And again, I can explain this if you do quick thinking. Like, remember, c is my function. So this is saying the function is just a flat line. So then as you approach anywhere on this line, the y value is the limit, the y value is always going to be that constant. So those are kind of our two key ones. They're going to come up on the next page. Let's do this next question. So now let's start working on limits. So, okay, find the limit of this function as x approaches 5. Okay, so what you could do is use the things I just showed you. So if you have a bunch of functions being added and subtracted, you can look at the limit of each function separately. So when I see this, I see, okay, my first function is x squared. So what's the limit of x squared? Plus the limit of 2x minus the limit of 3. And all of those are as x approaches 5. Okay, now you can look at some other properties. Like another property was, okay, limit of something squared. Well, you can just look at, you can square the whole limit. So I could do this. Find the limit as x approaches 5 of x all squared. I factor out the 2. That was another property I had, right? I can move the constant out of the limit. So I get 2 limit x approaches 5, and that would all be in the bracket, minus the limit of 3 x approaches 5. Now watch this. Limit of x as x approaches 5. Well, that's one of the important ones I just showed you. The limit of x as x approaches a is a. So the limit of x as x approaches 5 is 5. So I end up with 5 squared. Okay, then over here, the limit of x as x approaches 5. So this is going to be plus 2 times 5. And this last one, the limit of 3 as x approaches 5. Well, just look at that. The limit of a constant, like 3, as x approaches 5 is just that constant. So this is 3. That gives me 25 plus 10 minus 3. That gives me 32. Now, again, I don't want to spend too much time on this. This is obviously not the way we're going to solve these, because it's kind of annoying to have to do this. And you've probably guessed it would have been a lot easier. Hey, Mr. Claudia, why didn't you just sub in the 5? Right? Oh, yeah. Sub in x equals 5. So in other words, the limit as x approaches 5, x squared plus 2x minus 3, that's equal to just sub the values in. So I have 5 squared plus 2 times 5 minus 3, which I know is 32. This is called direct substitution, right? That's what I wrote here, direct substitution. And it's completely valid. And it makes sense, right? If you go back to this example, with a great normal continuous function, the limit and the y value are the same. So you could just sub in the number. Look at the notation too. You probably haven't talked about this yet, but we write lim, so we kind of write that in a cursive. Then underneath it, I write what x is approaching, and then I have the function in brackets if necessary. Once I've subbed in the number, I no longer write limit because I'm just solving for the value, which is 32. So the lim disappears. Now, direct substitution is great, and it works. However, look back at our first few examples. This strategy of direct substitution did not work here, right? If I had just said, oh, sub in 3, it doesn't work. You get indeterminate form. So this is a great strategy, that is to find the limit as x approaches a of f of x. Well, I can just sub in a, so into the function. This only works, direct substitution, if f of x is continuous. Continuous at a. Hopefully you learned this idea of continuous or continuity last year. This means no holes or asymptotes. No funny business. None of those things that stress us out. Just the curves that we miss from our youth in grade 9 and the beginning of grade 10. So let's do some examples and see how this works. So I have a limit. I want to find the limit of this function as x equals 4. X approaches 4. So I'm going to try direct substitution. So I get rid of the lim, and now I replace all the x's with 4. So 4 squared minus 16, 4 minus 4. What's my problem? I end up with 0 over 0. I end up with some divide by 0 situation. This does not exist. You cannot divide by 0. So then how do I find the limit of this function as x approaches 4? Well, what you have to do is you have to use a math trick to try to simplify the limit. And hopefully you see that one of the tricks right in front of you, like this x squared minus 16 is a difference of squares. So the limit as x approaches 4 of x squared minus 16 over x minus 4. So the trick I'm going to use here is I'm going to factor the numerator. So I end up with a difference of squares, x plus 4, x minus 4 over x minus 4. My trick, factor the numerator. Okay, now look what happens when I factor the numerator. I can cancel these out, divide these out. So now my limit has simplified, it's still a limit, to x plus 4. And you should put the brackets, otherwise you're just saying limit of x plus the value 4. Okay, now I can do direct substitution. When I do that, I replace the x with 4. So my answer is 8. So this last step, direct substitution, and notice how direct substitution. Notice how the limit sign disappeared once I did the direct substitution. I got the answer 8. So that means that for this function, at x equals 4, the function doesn't exist. There's some sort of discontinuity, a hole or an asymptote. But as x gets closer and closer and closer to 4, it is approaching, the y value is approaching 8. So actually there's a hole there. Okay, so hopefully you see this is going to be kind of fun. You try direct substitution. If it doesn't work, then you can factor, use some sort of trick. And usually it's factoring, but I'll show you the 4 types of trick, or the other types of tricks. So here we go, this first one. What trick? Well, I could factor the, oh wait, I could just do direct substitution. So if you can do direct substitution, do it. Don't like try to overthink it. Remember, IB tends to give you simpler questions than you'll expect. That most of their limit questions will be related to direct substitution. It's only more my tests that you're going to see. You're going to see other questions. So I end up with -3/3, and I get -1. So we have a direct substitution here. And note, do not write limit notation, limit x approaches 1 after substitution. So notice my notes how I got rid of the limit sign once I sub to the number. Okay, let's do the next question. So I have limit as x approaches 2, x cubed minus 8x squared. Okay, so can I sub in 2? I get 4 minus 12 plus, no, I cannot sub in, sorry, 4 minus 6 plus, yeah, I cannot sub in 2, so I have to do some sort of math trick. Well, I'm going to factor. Now, normal year, I think you would have learned this difference of cubes. I believe this year you haven't learned difference of cubes. So I'm not going to test you on this because it's not an IB, difference of cubes, but I'll just show you the lesson like it's normally done. So the limit as x approaches 2, well, the way I would factor this is it becomes x minus 2 because it's a difference of cubes. And then what I'm left with is x squared plus 2x plus 4. This is kind of a formula you would need to memorize last year usually. The bottom, on the other hand, you should be able to factor regardless. That's, well, to get positive 2, I need a, oh yeah, this needs to be -1 and -2. Let me put over here your formula for difference of cubes. So if you have a cubed minus b cubed, that factors to a minus b, which is easy enough, and then a squared plus ab plus b squared. Oops, oh, we can't see that. And so that's what I applied right here, right? I have x, a is x, and b is 2, so I have a minus b, x minus 2, then a squared plus 2x plus 4. You do not need to know this. I'm not going to test you on this year because you did not learn it last year. And IB does not require you to know this. So like, this question is kind of like a fun freebie. You're getting more for your education. These two now cancel out, so I'm left with limit as x approaches 2 of x squared plus 2x plus 4 over x minus 1. Now I can do direct substitution, so I end up with 2 squared plus 2 times 2 plus 4 over 2 minus 1. That gives me 4 plus 4 plus 4 over 1, so that gives me 12. That's my limit. The cousin of the difference of cubes is the sum of cubes. So if I have a cubed plus b cubed, this is similar, so a plus b, but there is a trick at the beginning. It's a squared minus ab plus b squared. So this is the kind of the unintuitive one. Oh, sorry, this is plus. This is negative here. Again, you're not going to have to know these, so I'm just writing him here. So when I show this video, the future people in the future who don't have COVID restrictions on their course, they'll know how easy your job was. Okay, let's do these questions. These will be on my sort of test. I have a limit, and if I sub in 0, I've got a big problem. Now, I can't factor this, but I can do the opposite, which is expand or FOIL the numerator. So this limit, I'm going to FOIL the numerator. So I end up with 2 times 2, which is 4, 2 times h plus 2 times h, which is 4h, and then h times h, which is h squared, minus 4 over h. This is called expanding or FOILing the numerator. Now, when I do this, 4 minus 4, those things subtract out. They subtract to 0. So I'm left with, my limit simplifies to 4h plus h squared over h. And I hope you see the great thing that's happening here. I can factor an h out of the numerator, and I end up with 4 plus h over h. So I did a little bit of simplifying, I factored, and now I can cancel out, divide out those h's, one on the top, one on the bottom. So my limit now has simplified to 4 plus h, should be in bracket. Okay, and now I can do direct substitution. I sub in 0, so I end up with 4 plus 0, so my answer is 4. So this question, what trick did you have to use? I had to expand FOIL, and then I had to do some factoring. The last type of question you can get, and this is probably the hardest, but there's only really 3 types of questions, right? Factor, direct sub, factor, FOIL, and then this type. You have a question like this. Can I limit like this? Can I sub in x equals 0? No, because then I have a divide by 0 question. Okay. Can I simplify this? Expand? No, I can't. But what I know this is that my numerator has a square root here. And then a subtract 1 or a plus 1. In this case, a subtract 1. I'm going to multiply by something called the conjugate. I'm going to try to turn this into a difference of squares. So I have something minus something. Remember, the other factor for a difference of squares would be that something plus something. Now, if I multiply the top by that, I have to also do it to the bottom. Otherwise, I'm just making up math. Watch what happens when I do this. I've just created a difference of squares. I have the x plus 1 squared minus 1 squared over, and the denominator is still a mess. It's x times root x plus 1 plus 1. So this is called multiply by the conjugate. I'm going to put in bracket, it creates a difference of squares. So now, right, because I have this and this, so I would have the square, and I have this and this and the square, and it's a minus. So now look, I can simplify this. This square root squared just gives me that thing, and 1 squared is just 1. The denominator, sadly, still a mess. But look at this great news. 1 minus 1, well, they subtract out to 0. So I'm left with, my limit simplifies to x over x. Unfortunately, the denominator is still a mess. But look what I have now. I have an x divided by an x. Those two things divide out. So my limit simplifies to 1 over square root of x plus 1 plus 1. Now, and finally, I can put in, for direct substitution, 0 square root of 0 plus 1 plus 1. Even though the denominator is a mess, I can solve this. It's 1 over square root of 1, which is 1 plus 1. So the answer is 1 over 2. So those are my limits. It's a really odd concept. I get a lot of questions about this. I know you'll have questions when I see you. The easiest way to solve is by direct substitution, but where that's not possible, you have to use math tricks. The math tricks you might have to use are factoring, not these on your in this current year, but all your other factoring tricks. Another option you might have to do is expanding the numerator, and then you have this conjugate, which is kind of the most challenging type. Your homework is a separate sheet of paper. It's not in your textbook. And it's number 2 to 6. There are a lot of them, so it will be A, C, E, G, I. So good luck with those, and we'll see you next time.